If there was no liquid, things would just sit around separately. You need this constant interaction and you need a different chemical mix. And water does all of that.
And so a lot of our searches for life-like planets or Earth-like planets outside our solar system are based on this sort of primary assumption that we need liquid water.
We've long thought Earth has liquid water because of its unique position in the solar system.
It's right in this zone that we call the habitable zone, where the sunlight can support liquid water on the surface of the planet.
Too close to a star, and water boils off a planet's surface. Too far away, and water freezes solid. For decades, this has been the standard theory.
We used to think that the habitable zone around a star was the only place to find liquid water, but once again, nature has surprises for us.
But we have now discovered that liquid water might exist in places we never expected. In 1998, a meteorite crash lands in Texas. Today, scientists at Arizona State University are still studying its secrets.
We had no idea that it would contain this really, really spectacular finding.
It contains a mysterious purple mineral. The exotic color comes from exposure to cosmic radiation, but the compound itself is very ordinary.
It's actually sodium chloride, which is essentially the same mineral as table salt. But what's really cool is that it actually contains little globules of liquid water. And that liquid water was trapped in these crystals 4.5 billion years ago.
In 2018, scientists re-examined the crystals and discovered the liquid water wasn't traveling alone.
We've now actually found organic compounds in association with this liquid water in these salt crystals. And that's something that's really new and really spectacular.
We actually found amino acids, the building blocks of all of our proteins, even our DNA, and we found liquid water, the very building blocks of life, inside a meteorite.
So could life exist somewhere else in our solar system? A NASA mission to Saturn turned up some shocking results. The Cassini space probe flew beneath Saturn's moon, Enceladus.
Enceladus, no one cared about. It was a tiny little snowball of a world.
But Enceladus surprised everyone. Geysers of liquid water, dozens of them, blast out of trenches along the moon's surface, coming from a vast subsurface ocean. But how is it possible that this remote frozen world, well outside the habitable zone of our sun, has liquid water?
When you get into the outer solar system, it's cold, right? There has to be some energy source, something keeping it hot.
Experts think the energy comes from the powerful gravitational grip of the giant gas planet. It's a theory called tidal heating.
As it orbits the main planet, as it's moving around and the gravitational pull occurs, there's a lot of heat generated in the core, and that sustains this nice, warm ocean environment underneath that ice.
Oceans on Earth are full of life. Could the same be true of Enceladus?
I'm a big fan of Enceladus. I think it's by far and away the best place to go to search for evidence of life.
In 2018, researchers analyzing the Cassini data discovered that the plumes of Enceladus contain complex organic molecules.
Just simple molecules, we find those, like methane. But the Cassini results are showing that there are these more complex, larger organic molecules as well.
This is the first detection of complex organics on an extraterrestrial water world.
All of a sudden, Here's water jetting out, carrying organic material, all the ingredients needed for life. It was like too good to be true.
But Enceladus isn't the only small world with a subsurface ocean. Other moons and dwarf planets have liquid water too.
We think the most important thing for life to form is the presence of liquid water, and our solar system seems to be full of it.
The discovery of liquid water in the outer solar system changes the rules of how life might originate in the universe.
Across the universe, alien life could be hiding underneath the surface.
Internal water oceans are far more common than surface water oceans. So if there is a lot of life out there in the universe, chances are it's in an internal ocean under miles of ice.
Who knows what might be lurking inside icy exoworlds?
There may be jellyfish and octopuses all over the place in exomoons and exoplanets under ice that have civilizations that we just don't know about.
Finding liquid water oceans could open up a world of possibilities.
If you're not excited about intelligent extraterrestrial octopus civilizations, I don't know what to say.
The chances of finding life in our solar system just got a heck of a lot better. Building blocks and liquid water are common. But you need more than just these two conditions for life to take hold. Life needs a spark.
Life appears to need some form of energy to actually get the molecules interacting.
One thing that may have helped kickstart life on Earth is ultraviolet radiation from the sun.
Ultraviolet light is emitted by all stars. There are billions of stars in our galaxy. Can life get started around any star? Or is our sun unique? Earth is a solar-powered planet. At the bottom of the food chain, plants use photosynthesis to convert sunlight into chemical energy, food for the rest of us.
I like eating both grass, essentially wheat, and I also fancy the odd hamburger from a cow that is eating that grass. So this whole ecosystem is powered by sunshine.
But recent studies have shed new light on how life developed under our sun. Specifically, the role of ultraviolet light.
UV radiation is useful for breaking molecules up and triggering reactions. Maybe that played a role in the origin of life.
It breaks down simple organic molecules, and then they can rebuild themselves into things that are more complex. If you do that over and over again, eventually you somehow get life.
Scientists think life on Earth started around 4 billion years ago. A time when Earth's atmosphere gave little protection. UV radiation levels were 100 times higher. Was UV essential for the development of life's code, DNA?
We know that life on Earth stores information in DNA and then uses that information to build proteins. So we have the blueprints and the bricks. The blueprints are the DNA and the bricks are the proteins.
But we think that the first life on Earth, we used a chemical which is much simpler.
This simpler chemical was RNA, DNA's single-stranded forefather.
RNA is almost like a 2-for-1 offer. It does both of the fundamental things you need for a cell in the same compound.
So it was simultaneously the bricks and the blueprint.
Unlike other molecules, RNA is more resistant to the high UV environment of early Earth, allowing it to flourish. RNA eventually evolved into DNA, and life started.
To have life on the planet, one important consideration is a certain amount of light that's going to be needed, and a certain type of light that's going to be needed.
If all stars emit UV radiation, can life start anywhere?
When we think about looking for places that are conducive for life, we want to find a planet that might have enough UV radiation, so the star is bright enough or close enough that it's providing enough energy to the surface for life, but we also don't want to have too much UV radiation.
It seems that you need just the right amount of UV. The most common stars in the galaxy are red dwarf stars.
If red dwarf stars can harbor life on planets around them, there's an awful lot of real estate like that in our galaxy.